What if I told you there are objects in the universe moving so fast they could cross the entire United States in less than a second? Out in the vast cosmic ocean beyond our solar system, there are celestial speed demons racing at velocities that defy human comprehension. These aren't just fast, they're tearing through space with the kind of energy that rewrites the rules of physics as we know them. Picture a star flung from its galaxy like a cosmic slingshot, barreling through the void at millions of miles per hour. Or a spinning pulsar, a dense stellar corpse, hurling beams of radiation across space so rapidly they could outpace a lightning bolt. These aren't science fiction, they're real, and they're reshaping our understanding of the universe's extremes. Today, we're diving deep into 30 of the most astonishing speed records set by cosmic phenomena. From hypervelocity stars ejected by supermassive black holes to particles that flirt with the very speed of light itself, the universe is far wilder than we ever imagined. Ever heard of a quasar, a jet of superheated plasma shooting from a galaxy's heart, moving so fast it could lap Earth's orbit in mere minutes? Or what about rogue planets wandering the darkness at speeds that would leave our fastest rockets in the dust? Each of these cosmic speedsters holds secrets about how gravity, energy, and time itself behave under conditions we can barely replicate on Earth. But why should this matter to you? Because these aren't just distant curiosities, they're the universe's way of pushing boundaries, showing us what's possible when nature unleashes its full power. Understanding these extreme objects helps us decode the origins of galaxies, the fate of stars, and even the limits of Einstein's theories. And by the end of this journey, you'll walk away with a new appreciation for just how breathtakingly fast and how bizarre the cosmos truly is. So buckle up, we're about to take a ride through the fastest, most mind-bending corners of space, where the laws of physics get stretched to their absolute limits. Ready to have your mind blown? Let's go. Imagine a star moving so fast it could escape the entire Milky Way, not just drifting away, but hurtling out at nearly 2 million miles per hour. These aren't runaway stars nudged by chance encounters. They're hypervelocity stars, cosmic fugitives catapulted into intergalactic space by the most violent force in the universe, a supermassive black hole. Picture this scenario at the heart of our galaxy. A pair of stars orbit dangerously close to the Milky Way's central black hole, Sagittarius, a star. One gets captured, swirling into oblivion, while the other is flung outward like a stone from a slingshot, gaining insane speed from the gravitational recoil. Astronomers first spotted these extreme outliers in 2005, using telescopes to catch their faint light streaking through the void. Unlike most stars which follow predictable orbits, hypervelocity stars are on one-way trips, destined to leave their home galaxies forever. Some blaze trails so fast they'll eventually cross the incomprehensible gulf between galaxies, sailing alone through the freezing darkness. What makes them even more fascinating is their origin story. Not all hypervelocity stars come from black hole ejections. A few might be survivors of dwarf galaxies torn apart by the Milky Way's gravity, their stars flung like debris from a cosmic collision. Others could be the result of supernova explosions in binary systems, where one star explodes and the other is sent rocketing away. These stellar speed demons aren't just curiosities, they're celestial breadcrumbs, helping scientists map the hidden forces shaping galaxies. By tracking their trajectories, astronomers can reverse engineer their paths, uncovering clues about the black holes that launched them and the gravitational landscapes they've traversed. It's like watching sparks fly from a spinning grindstone. Each one tells a story of the forces that set it free. And here's the kicker: some hypervelocity stars might even be carrying planets with them. Imagine a world orbiting one of these exiled stars, bathed in perpetual twilight as it races into the endless void. Talk about the ultimate cosmic road trip. So next time you look up at the night sky, remember, Out there, stars are moving faster than anything humans have ever built, rewriting the rules of where celestial objects can go and how fast they can get there. But even hypervelocity stars can't hold a candle to the dizzying spin of millisecond pulsars, stellar remnants so dense they pack the mass of our sun into a city-sized sphere, rotating hundreds of times per second. Picture a cosmic blender spinning so fast its surface moves at a quarter the speed of light. These neutron stars are born from the explosive deaths of massive stars, their cores collapsing into ultra-dense spheres during supernova explosions. When such a star implodes, it conserves its original angular momentum but shrinks dramatically, causing its rotation to accelerate to mind-bending speeds, like an ice skater pulling their arms in during a spin, but on a cosmic scale. Take Pulsar J1748-2446 AD, one of the fastest known pulsars, whirling at 716 revolutions every second. At that rate, its equator races at nearly 52 million miles per hour. If you stood on its surface, impossible. Given its crushing gravity, you'd experience forces so extreme your atoms would be torn apart. These pulsars aren't just spinning rapidly, they're also precision cosmic lighthouses emitting beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like an interstellar strobe light, producing rhythmic pulses detectable from thousands of light years away. What's even more fascinating is how some pulsars reach such extreme speeds. While newborn pulsars rotate quickly, millisecond pulsars get an extra boost by siphoning material from a companion star. As gas spirals onto the pulsar's surface, it transfers angular momentum, revving it up like a turbine. Over hundreds of millions of years, this process can accelerate a once slow pulsar to breakneck velocities. Scientists use these cosmic metronomes for groundbreaking experiments. Their precise pulses act as natural laboratories for testing Einstein's theory of general relativity, revealing how gravity warps spacetime. Some millisecond pulsars even rival atomic clocks in their regularity, offering potential navigation tools for future space travel. And in rare cases, pairs of pulsars orbiting each other emit gravitational waves, ripples in spacetime that observatories like LIGO can detect. Yet for all their precision, pulsars aren't eternal. Over billions of years, their spins gradually slow as they radiate energy away. But even in their decay, they leave behind clues about the universe's most violent events: supernova, collisions, and the turbulent lives of stars. Next time you hear about a flickering pulse from deep space, remember, you're witnessing the aftermath of a stellar explosion, spinning faster than a kitchen blender and illuminating the cosmos with every rotation. If hypervelocity stars and spinning pulsars seem fast, they're practically standing still compared to the cosmic particle accelerators lurking in the hearts of galaxies. Picture a supermassive black hole millions of times heavier than our sun, devouring everything that strays too close. But not all that matter gets swallowed. Some gets hurled back into space at nearly the speed of light, forming jets of plasma so powerful they stretch across millions of light years. These are relativistic jets, nature's ultimate particle cannons, and they are some of the fastest phenomena in the known universe. At the center of galaxies like Messier 87, which famously hosted the first ever image of a black hole's shadow, these jets erupt with unimaginable force. Charged particles, mostly electrons and protons, get whipped around the black hole's accretion disk, a swirling vortex of superheated gas. As they spiral inward, the black hole's insane gravity and its magnetic fields act like a cosmic slingshot, launching material outward along the poles at velocities reaching 99% light speed. That's so fast, if you could ride one of these jets, you'd circle Earth 7 times in a single second. What's truly mind-blowing is how these jets maintain their structure over staggering distances. The Chandra X-ray Observatory has captured images of jets extending far beyond their host galaxies, some spanning lengths equivalent to 50 Milky Ways placed end to end. Despite traveling through the near-perfect vacuum of space, the particles in these jets don't scatter wildly. Instead, they're funneled into tight beams by the black hole's magnetic fields, acting like an invisible highway guiding the particles across intergalactic space. The energy involved is almost beyond comprehension. A single jet can outshine its entire host galaxy, emitting radiation across the spectrum, from radio waves to gamma rays. When these jets slam into surrounding gas clouds, they create shock waves that heat the material to millions of degrees, glowing brightly in X-rays and visible light. Some even produce high-energy neutrinos, ghostly particles that pass through entire planets without slowing down. But these jets aren't just cosmic fireworks, they play a crucial role in shaping galaxies. By injecting energy into their surroundings, they regulate star formation, preventing gas from cooling and collapsing into new stars. Without them, galaxies might look drastically different, clumping into denser, more chaotic structures. They're proof that black holes aren't just destroyers, they're also architects, sculpting the universe on the grandest scales. And here's the wildest part: we might owe our existence to these jets. By stirring up galactic gas and enriching it with heavy elements, they've helped create the conditions for planets and life to form. So the next time you hear about a black hole's destructive power, remember, those same forces might have set the stage for everything we know. Now let's zoom in from galaxy-sized jets to something unimaginably small yet just as fast: cosmic rays, subatomic particles screaming through space at nearly the speed of light. Among them is the legendary Oh My God particle, a single proton that slammed into Earth's atmosphere in 1991 with so much energy it left scientists speechless. Picture this: a particle smaller than an atom, carrying the kinetic energy of a baseball hurled at 60 miles per hour. That's like a grain of sand hitting you with the force of a freight train. These cosmic bullets don't just break speed records, they defy logic. The Oh My God particle was moving at 99.999999999% the speed of light, just a hair's breadth below the universe's ultimate speed limit. At that velocity, time dilation gets extreme. For the particle, the journey across the Milky Way would feel like minutes, while billions of years pass for the rest of the universe. Where do they come from? That's one of astrophysics' biggest mysteries. Some might be flung from supernova remnants, where shockwaves act like natural particle accelerators. Others could originate near supermassive black holes or colliding galaxies, where turbulence and magnetic fields whip particles to insane speeds. There's even speculation about exotic sources like cosmic strings, hypothetical defects in spacetime left over from the Big Bang. When these particles strike Earth's atmosphere, they trigger cascades of secondary particles called air showers, which detectors like the Pierre Auger Observatory can trace. But here's the twist: the highest energy cosmic rays are so rare, scientists might detect only 1 per square kilometer per century, and their paths are scrambled by galactic magnetic fields, making it nearly impossible to trace them back to their origins. What's at stake? These particles are nature's way of testing physics at energies far beyond what human-made colliders can achieve. They might hold clues to dark matter, extra dimensions, or even flaws in Einstein's relativity. Imagine a single proton carrying the secrets of the universe's most violent events, and it's been raining down on us all along, unnoticed. So the next time you feel a raindrop, remember, somewhere in that same sky, an invisible particle might be streaking past at nearly the speed of light, carrying the energy of a cosmic explosion straight from the depths of space. And we're just beginning to unravel what it's trying to tell us. Quasars aren't just the brightest beacons in the cosmos, they're also some of the most destructive. Picture a supermassive black hole, billions of times the mass of our sun, gorging on gas and dust. As material spirals inward, it heats up to millions of degrees, glowing brighter than an entire galaxy. But that's not the most extreme part. some of that infalling gas doesn't get swallowed, it gets blasted back into space in colossal outflows, screaming outward at 20% the speed of light. That's over 130 million miles per hour, fast enough to cross the distance between Earth and the Moon in just 2 seconds. These quasar outflows aren't gentle breezes, they're cosmic hurricanes carrying enough energy to sterilize whole galaxies. Imagine a shockwave so powerful it can strip away star-forming gas, leaving entire regions of space barren. Astronomers have detected these outflows stretching tens of thousands of light years, far beyond their host galaxies. The force is staggering. A single quasar can eject more material in a year than our Sun will produce in its entire 10 billion-year lifetime. Here's the paradox: these violent outflows don't just destroy, they shape the universe. By heating and dispersing cold gas clouds, quasars act like cosmic regulators, putting the brakes on runaway star formation. Without them, galaxies might burn through their fuel too quickly, forming too many stars too soon and collapsing into chaos. Some theories even suggest quasar outflows helped create the conditions for galaxies like ours to evolve steadily, avoiding an early burnout. But how do they work? Magnetic fields around the black hole twist and channel some of the infalling material into narrow jets, while radiation pressure from the quasar's intense light pushes other gas outward in a wider, more chaotic outflow. The result is a feedback loop. The black hole's feast fuels its own fury, which in turn controls how much fuel remains for future feasts. We're seeing echoes of this process in distant galaxies, where quasars flicker like cosmic lighthouses, their outflows carving vast bubbles in surrounding gas. Some of these bubbles are so large they could contain dozens of Milky Ways. And here's the wild part: the same outflows that suppress star formation might also trigger it elsewhere, compressing gas clouds at their edges and sparking new stellar nurseries. Quasars remind us that destruction and creation are two sides of the same coin in the universe. Their outflows are like cosmic gardeners, pruning galaxies to keep them from growing too wild, proof that even the most violent forces in space can have a surprising touch of elegance. Even black holes, the universe's ultimate vacuum cleaners, aren't always stationary. Some get kicked across space at staggering speeds, leaving destruction in their wake. Hubble Space Telescope images reveal eerie dark streaks slicing through cosmic gas clouds like scars from a celestial hit and run. These are the trails of runaway supermassive black holes, some barreling through space at 5 million miles per hour, fast enough to travel from Earth to the Moon in under 3 minutes. How does something with the mass of millions of suns get moving that fast? The answer lies in galactic collisions. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance. If they don't collide directly, the complex interplay of forces can slingshot one black hole outward at incredible speeds. Imagine two whirlpools merging in a bathtub. The swirling chaos can eject a jet of water with surprising force. On a cosmic scale, that jet is a black hole weighing billions of tons, flung into the void by gravity's recoil. One famous example is the object nicknamed the Cosmic Bullet, a supermassive black hole caught racing through its galaxy 3.5 billion light-years away. Hubble images show a bright quasar, the black hole's glowing accretion disk offset from its host galaxy's center, with a long trail of young stars stretching behind it like a cosmic wake. This stellar tail forms as the black hole plows through gas clouds, compressing them so violently that new stars ignite in its path. It's the astronomical equivalent of a speedboat creating waves, only here the waves are entire star clusters. But here's where it gets stranger. Some ejected black holes might be completely invisible, no quasar, no trail. If a black hole gets kicked before accumulating enough gas to glow, it becomes a dark predator drifting unseen through intergalactic space. Simulations suggest thousands of these rogue black holes could be lurking between galaxies, their presence betrayed only by subtle gravitational distortions when they pass near visible objects. The implications are mind-bending. A wandering supermassive black hole could theoretically approach a galaxy unnoticed, its gravity disrupting orbits before settling into a new center of power. Some astronomers speculate this might explain odd features in certain galaxies, like off-center nuclei or unexpected star formation patterns. And if two runaway black holes crossed paths in intergalactic space, they'd form a binary system, circling each other for eons until finally merging in a burst of gravitational waves, a collision so powerful it would briefly outshine every star in the universe. These discoveries challenge our assumptions about cosmic stability. Even the most massive objects aren't anchored in place. They're subject to the same chaotic dynamics that govern the rest of the universe. So next time you see a Hubble image of a peculiar gas cloud or an oddly shaped galaxy, consider the possibility, somewhere in that frame, a trillion-ton fugitive might be racing through the dark, rewriting the rules of cosmic motion. Two neutron stars spiraling toward each other at a third the speed of light sounds like science fiction. But in 2017, astronomers witnessed this exact scenario unfolding 130 million light-years away. This wasn't just a spectacular collision. It was a cosmic gold factory in action, a violent merger that answered century-old questions about where the universe's heaviest elements come from. The event, catalogued as GW170817, sent ripples through space-time so profound they were picked up by gravitational wave detectors on Earth, marking the first time humanity had observed both gravitational waves and light from the same cataclysm. Imagine two city-sized objects, each more massive than our Sun, whirling around each other hundreds of times per second before slamming together. The energy released was incomprehensible. For a brief moment, the merger outshone every star in the observable universe combined. But the real magic happened in the aftermath. The collision forged enough gold, platinum, and uranium to outweigh 30 Earths, scattering these precious metals into space in a glowing cloud of radioactive debris. Every gold ring on Earth, every platinum catalytic converter, even the uranium-fueling nuclear reactors, they all likely owe their existence to similar neutron star smash-ups scattered across cosmic history. LIGO gravitational wave detectors caught the first whispers of this event as space-time itself stretched and compressed like a trampoline underfoot. Within hours, telescopes worldwide swiveled toward the source, capturing a kilonova, a fiery, jewel-toned explosion unlike anything seen before. The glow came from radioactive decay of freshly minted heavy elements, a celestial alchemy show confirming theories first proposed decades earlier. What makes neutron star mergers unique is their precision as cosmic laboratories. Unlike black hole collisions, which leave only gravitational waves as breadcrumbs, neutron star crashes eject visible matter, allowing scientists to study both the invisible fabric of space-time and the chemical fingerprints of newly forged elements. The 2017 event even settled a debate about gamma-ray bursts short, intense flashes once thought to originate from unknown sources. This kilonova proved they're the birth cries of newborn black holes, as the merged neutron stars likely collapsed into one within milliseconds. But here's the twist. These mergers are vanishingly rare in any given galaxy, happening maybe once every 100,000 years. That makes GW170817 a stroke of cosmic luck, close enough to detect, yet distant enough to observe safely. Future collisions will help unravel lingering mysteries, like why some neutron stars seem to have squishier interiors than others, or whether these events are the primary source of all cosmic heavy elements. So next time you hold a piece of gold jewelry, remember, it's not just a metal, it's stardust forged in one of the universe's most extreme crucibles, a relic of neutron stars dancing their final, deadly tango across the cosmos. Galaxies aren't just drifting apart, some are rocketing away so fast their light will never reach us. This isn't science fiction. It's the unsettling reality of our expanding universe, where space itself stretches faster than light can traverse it. Picture a half-deflated balloon covered in dots. As you blow it up, every dot moves away from every other dot. Now imagine those dots are galaxies, and the balloon is the fabric of space-time, inflating relentlessly since the Big Bang. The farther apart two dots are, the faster they separate as the rubber stretches between them. Here's where relativity gets turned on its head without breaking any rules. When we say distant galaxies recede faster than light, it's not because they're moving through space at impossible speeds. Space itself is expanding beneath them, carrying them away like raisins in rising bread dough. This cosmic loophole means no object is overtaking light in its local environment. Instead, the cumulative stretching across vast distances adds up to apparent superluminal speeds. Take GNZ 11, one of the most distant galaxies ever observed. Its light took 13.4 billion years to reach us, but due to expansion, the galaxy itself is now 32 billion light-years away. That means space has stretched so dramatically in transit that GNZ 11 is currently fleeing at more than twice light speed relative to us, not by moving, but by the relentless growth of the space between us. This expansion has startling consequences. About 94% of observable galaxies are already racing away faster than light can bridge the gap. Their light emitted today will never reach Earth, their stories forever lost as the stretching spacetime redshift shifts their signals into oblivion. Future astronomers won't see these galaxies at all. The Milky Way's local group will appear utterly alone in a darkening void. Yet Einstein's relativity remains intact because no information travels faster than light locally. It's the large-scale geometry of spacetime that changes the rules, proving the universe is stranger than we imagined. That balloon analogy, it's already obsolete. Our universe expands at an accelerating rate, meaning those galaxy dots aren't just drifting apart but doing so ever faster under dark energy's mysterious push. So when you gaze at Hubble's deep field images, remember, each speck represents a cosmic island being carried away by the tide of space itself. They're like the faint postcards of a universe we're losing touch with, one expansion at a time. Deep in the cosmic static, there are flashes so brief you'd miss them in the blink of an eye, yet so powerful they outshine entire galaxies for a millisecond. Fast radio bursts, or FRB, are among the universe's most enigmatic speed demons. These hyper-energetic pulsars race across billions of light-years, packing more energy than the sun emits in 80 years into a burst shorter than a coffee break. The first one was discovered by accident in 2007, buried in old telescope data, a spike so intense astronomers initially doubted its cosmic origin. Now we know these flashes are real, and they're rewriting the rules of high-energy astrophysics. What makes them truly bizarre is their frequency sweep, like a cosmic slide whistle. As an FRB travels through the vast gulfs between galaxies, its high-frequency waves arrive slightly earlier than the low-frequency ones, stretched out by interactions with sparse electrons in intergalactic space. This dispersion is like a fingerprint, revealing how much material the burst has plowed through to reach us. Some FRBs show patterns so extreme they must have traversed half the observable universe, carrying whispers from epochs when the cosmos was barely half its current age. Theories about their origins range from plausible to downright sci-fi. Leading candidates include Magnetar's ultramagnetic neutron stars capable of starquakes so violent they crack open magnetic field lines, releasing tsunamis of radio waves. In 2020, astronomers caught one red-handed, a Milky Way magnetar firing off an FRB-like burst, albeit weaker than the extragalactic monsters. Other explanations involve collapsed stars reigniting, black holes shredding neutron stars, or even cosmic strings, hypothetical spacetime defects left over from the Big Bang. Then there's the elephant in the room. Could some FRBs be artificial? The notion isn't entirely dismissed. A repeating FRB from 3 billion light-years away cycles every 157 days like clockwork, sparking debates about engineered beacons. But Occam's razor favors natural, if spectacular, astrophysics. After all, the universe has no shortage of ways to whip up unimaginable energies without invoking alien megastructures. What's clear is that FRBs are cosmic Rosetta Stones. Their dispersion measures act as probes, letting scientists tally the universe's missing matter, the diffuse gas too faint to see directly. Some bursts even exhibit scattering, hinting at turbulent halos around galaxies they've pierced. And because FRBs come from all directions, they're painting a three-dimensional map of the cosmos' large-scale structure. Yet mysteries abound. Why do some FRB sources repeat while others vanish forever? How can certain bursts spit out multiple frequencies simultaneously, defying emission models? Each new detection peels back another layer, proving that even the universe's briefest flashes can illuminate its deepest secrets. So the next time you hear about a blip in a radio telescope, remember, it might be the dying scream of a magnetar, the birth cry of a black hole, or something stranger still, racing toward us at light speed from the edge of everything we know. The sun might seem calm from our earthly vantage point, but its surface is a constant battlefield of magnetic explosions. And when those eruptions unleash solar flares, they can hurl protons across space at speeds approaching 80% of light speed. Picture a single proton, a speck smaller than an atom, rocketing fast enough to circle Earth's equator 7 times in 1 second. These aren't just cosmic curiosities, they're potentially deadly projectiles for anything or anyone in their path. Solar flares occur when the sun's tangled magnetic field lines suddenly snap and reconnect, releasing energy equivalent to 1 billion hydrogen bombs in minutes. The most violent flares, classified as X-class, act like particle accelerators the size of planets, boosting protons to relativistic speeds. During the Bastille Day flare in 2000, particles reached 80% light speed in under 10 minutes, so fast they overtook the light from the flare itself, arriving at Earth before astronomers even saw the eruption. The danger lies in their penetration power. Unlike ordinary radiation, these high-energy protons can slice through spacecraft hulls and spacesuits, depositing energy deep into human tissue. Astronauts caught outside shielding during such an event would absorb radiation doses comparable to standing next to a nuclear explosion. Even the International Space Station, with its partial protection, must occasionally retreat to more shielded areas when solar storms brew. Unshielded satellites fare worse. Their electronics can be fried by single particle strikes, causing malfunctions or permanent failures. Predicting these storms is a high-stakes game. Observatories like NAS, a solar dynamics observatory, monitor the sun's surface for telltale signs. Dark sunspots where magnetic energy builds, or sudden brightening in ultraviolet wavelength signaling an imminent eruption. When a flare detonates, the blast's X-rays reach us in just over 8 minutes, giving about an hour's warning before the most dangerous particles arrive. That's enough time for astronauts to take cover, but not enough to protect unhardened infrastructure. The real challenge comes from coronal mass ejections, often accompanying flares, which hurl magnetized plasma clouds toward Earth. These can amplify particle acceleration, creating prolonged radiation storms. In 2012, a Carrington-level ejection missed Earth by a week. A direct hit could have knocked out global power grids for months. Yet there's a silver lining. Studying these particles helps us understand fundamental physics. Solar protons serve as test subjects for how matter behaves under extreme acceleration, offering clues about similar processes around distant stars and black holes. And by tracing their paths through interplanetary space, we're learning to navigate the sun's invisible minefields, a skill that'll be crucial for future Mars colonists. So while solar flares remind us of our vulnerability, they also push us to innovate, turning a stellar hazard into a stepping stone for exploration. Hurtling through the Milky Way at 500,000 miles per hour, vast rivers of hydrogen gas stretch across thousands of light-years, cosmic nomads with enough fuel to birth millions of stars. These are hypervelocity clouds, and they're not just passing through, they're rewriting the story of how galaxies recycle material. Unlike the slow, drifting gas clouds within our galaxy, these intergalactic interlopers move with enough speed to escape gravity's grasp, leaving trails of ionized gas in their wake like cosmic contrails. Their origins are as dramatic as their speeds. Some might be remnants of dwarf galaxies torn apart by the Milky Way's gravity, their gas stripped away in violent tidal interactions. Others could be debris from galactic collisions ripped loose when the Andromeda Galaxy brushed too close billions of years ago. The most extreme cases might even be intergalactic gas clouds, hurled into our neighborhood by the gravitational tug of war between galaxy clusters. The Smith Cloud, a famous hypervelocity cloud just 40,000 light-years away, is barreling toward us at 700,000 miles per hour, carrying enough hydrogen to fuel 2 million suns when it eventually collides with the Milky Way's disk. What makes these clouds fascinating isn't just their speed, it's how they challenge our understanding of galactic ecosystems. As they plow through the Milky Way's outer halo, their hydrogen gas slams into existing material, creating shock waves that compress the gas and trigger star formation. Imagine tossing a boulder into a still pond. The ripples would churn the water, creating eddies where new structures form. On a galactic scale, that's exactly what hypervelocity clouds do, seeding pockets of star birth in their turbulent wakes. But it's not just about creation. These clouds also bring destruction. Their high-speed collisions can shred fragile molecular clouds, disrupting existing stellar nurseries before new stars have time to ignite. This push and pull dynamic creates a delicate balance in galactic evolution, where incoming gas can either spark new generations of stars or stifle them before they're born. Astronomers track these clouds using radio telescopes tuned to the faint glow of neutral hydrogen at 21 centimeters, a wavelength that slices through cosmic dust to reveal the invisible rivers of gas. Recent observations show some clouds are surprisingly metal-rich, hinting they originated not in the pristine voids between galaxies but in the hearts of ancient, shattered stellar systems. And here's the twist. Based on their trajectories, some hypervelocity clouds might eventually loop back around, falling into the Milky Way's disk to replenish its dwindling star-forming reserves. So the next time you look at the band of the Milky Way, remember, our galaxy isn't an island. It's a dynamic, ever-changing system fed by intergalactic currents racing through the darkness, each one carrying the raw materials for future suns, planets, and perhaps even life itself. What if the universe had speed limit breakers, particles born moving faster than light? Enter tachyons, the hypothetical speedsters that physicists have debated for decades. These aren't just fast, they're fundamentally different from anything we've observed, existing in a realm where the usual rules of motion get turned upside down. According to Einstein's relativity, nothing with mass can reach light speed, but tachyons, by definition, would always travel faster. They're like cosmic cheetahs starting the race already past the finish line. The math behind these phantoms emerges from quantum field theory as a quirk of equations. If you plug in an imaginary mass, yes, as in the square root of -1, you get particles that accelerate as they lose energy. Picture a tachyon losing steam instead of slowing down. It'd speed up, approaching infinite velocity as its energy drops towards zero. Bizarre, absolutely. But here's the kicker, their existence wouldn't necessarily shatter causality. While they could, in theory, send signals backward in time, some interpretations suggest they'd naturally avoid paradoxes by only interacting in self-consistent ways. It's like writing a letter to your past self. The universe might just crumple it up before it creates a contradiction. Why haven't we found them? Tachyons leave no obvious fingerprints. If they're electrically neutral, they'd zip through detectors unnoticed. Some theories even suggest they condensed out of the early universe's energy soup, becoming undetectable as space expanded. Yet their ghostly presence lingers in pop culture, from sci-fi warp drives to horror movies, as a symbol of physics' uncharted frontiers. The real value of tachyons lies in the questions they force us to ask. Could space-time have layers where different rules apply? Are we missing a hidden sector of particles operating beyond our perception? For now, they remain tantalizing what-ifs, reminding us that the universe's speed limits might have exceptions if only we knew where to look. At first glance, Hubble's images of V838 monocerotes seem to defy physics, a fiery shockwave expanding outward faster than light itself. But this cosmic magic trick, known as a light echo, is one of the universe's most breathtaking illusions. When this red supergiant erupted in 2002, it didn't actually blast material outward at superluminal speeds. Instead, the explosion's light bounced off layers of dust surrounding the star, reaching Earth via multiple scattered paths. The result, a seemingly impossible expansion where the echo races across space at up to 5 times light speed, a mirage created by geometry, not a violation of Einstein's laws. Think of it like standing in a foggy valley at night. If someone flashes a light, the beam hits nearby fog first, then illuminates more distant patches moments later. To an observer, it appears as if the light is moving outward faster than its actual speed, because the scattered reflections arrive delayed from different distances. V838's light echo works the same way, just on a stellar scale. The initial flash lit up a dust shell 1 light-year wide, but as that light traveled outward, it illuminated progressively farther dust layers. Hubble captured this progression over years, showing rings that seem to grow at impossible velocities. What makes these echoes more than just pretty pictures is what they reveal about the star's history. Each dust layer acts like a cosmic photo album, preserving snapshots of the star's past eruptions. By analyzing how light scatters through these layers, astronomers reconstructed V838's violent timeline, including evidence it experienced multiple smaller outbursts before its final cataclysm. The red hues dominating Hubble's images aren't just for show. They're literal starlight filtered through carbon-rich dust, telling us about the chemistry of the material expelled over millennia. Light echoes also serve as celestial measuring tapes. By tracking their expansion rate against known dust distances, scientists can calculate precise interstellar distances independently of traditional methods. It's like using a car's headlights to gauge the size of a tunnel, except here, the tunnel is light years long and the car is a dying star. Perhaps most mind-bending is how these echoes make time tangible. When we observe the rings, we're seeing the same explosion reflected from different epochs, like hearing an echo bounce off cliffs at varying distances. The innermost ring shows the light from 2 months post-eruption, the next from 6 months, and so on. It's as if the star's death throes were recorded on concentric celestial DVDs, each playing the same event at a slight delay. So next time you see Hubble's hypnotic images of V838's glowing halo, remember, you're not witnessing faster-than-light motion, but the universe's most grandiose sleight of hand, a reminder that sometimes reality's most dazzling tricks are just light, dust, and perfect timing. Gamma-ray bursts are the universe's ultimate fireworks, blinding flashes that outshine entire galaxies for a few fleeting seconds, yet pack more energy than our sun will produce in its entire lifetime. These cosmic detonations unleash narrow jets of plasma racing at 99.99% the speed of light, so focused they could hit a target a million light-years away with pinpoint accuracy. Imagine taking all the energy our sun radiates over 10 billion years and compressing it into a laser beam thinner than a straw. That's the raw, terrifying power of a gamma-ray burst's relativistic jet. The physics behind these beams reads like something from a superhero comic. When a massive star collapses into a black hole or two neutron stars merge, the resulting explosion channels energy into twin jets along the rotational axis, where magnetic fields act like cosmic particle accelerators. The jets are so concentrated that if one happened to point at Earth from across the Milky Way, its radiation could strip away our ozone layer in seconds. We've detected bursts so distant their light traveled nearly 13 billion years to reach us, meaning these explosions were rewriting cosmic chemistry when the universe was barely a toddler. What makes them truly bizarre is how they defy everyday intuition. Due to relativistic effects, time near the jet's core slows dramatically from our perspective. A minute-long burst might appear stretched over hours when observed slightly off-axis, while head-on, its light gets blue-shifted into lethal gamma rays. The afterglow, a fading echo across X-ray, visible, and radio wavelengths, reveals how the jets plow into surrounding gas, creating shockwaves that glow for weeks like cosmic embers. But here's the twist: we're only seeing a fraction of these events. Simulations suggest gamma ray bursts fire in all directions, but their narrow beams mean most miss Earth entirely. For every one we detect, 100 others might be lighting up distant galaxies unseen. Some could even be orphaned afterglows, jets initially pointed away that later curved toward us, leaving mysterious flares without an initial burst. These explosions aren't just celestial curiosities, they're galactic game changers. The heaviest elements in the universe, like gold and platinum, are forged in their crucibles. Their radiation might have influenced early life's evolution by triggering mutations. And on a cosmic scale, they've likely sterilized swaths of space, erasing any chance for life in their paths. Yet paradoxically, they've also seeded the cosmos with elements necessary for planets and biology to exist. The universe has a dark sense of irony. Its most destructive forces might also be its most creative. And gamma-ray bursts, they're the ultimate embodiment of that paradox: cosmic blowtorches that can obliterate worlds, yet light the way for new ones to form. Our galaxy isn't just drifting aimlessly through space, it's racing toward an unseen gravitational monster at 1.3 million miles per hour. This mysterious force, known as the Great Attractor, lurks about 250 million light-years away, pulling not just the Milky Way but entire clusters of galaxies toward it in a cosmic river of motion. Picture billions of stars, including our Sun, caught in an invisible current, funneled toward something so massive it bends the fabric of the universe itself. The story of its discovery reads like a cosmic detective thriller. In the 1970s, astronomers mapping galaxy motions noticed something odd. Everything in our local universe, thousands of galaxies, was streaming toward a single point in the constellation Centaurus. This wasn't just random drift, it was a coordinated migration, as if space itself was tilted toward some unseen slope. The Great Attractor's name was coined to describe this enigmatic focal point, but its true nature remained hidden behind the Milky Way's own galactic plane, a zone so thick with dust and stars it's like trying to peer through a blizzard. What makes this mystery even deeper is the realization that the Great Attractor isn't the end of the story. Beyond it lies an even larger structure, the Shapley supercluster, a gargantuan assembly of galaxies with a collective mass 10,000 times that of the Milky Way. This cosmic heavyweight might be the ultimate source of the pull, with the Great Attractor acting as just a waypoint in our galactic journey. Yet even Shapley can't fully explain the observed motions, leading some theorists to propose the existence of unfathomably large structures. Vast concentrations of dark matter and galaxies stretching across billions of light years, whose gravity orchestrates the flow of everything around us. Mapping this cosmic current is like tracing the veins of the universe. Astronomers use redshifts, the stretching of light as galaxies move away, to construct three-dimensional velocity maps, revealing how spacetime itself is being tugged. One stunning visualization shows thousands of galaxies color-coded by speed. their paths forming elegant filaments that converge like rivers feeding into a delta. This cosmic flow isn't just artistic, it's evidence of the universe's large-scale structure, a web of gravity woven by both visible matter and the unseen dark matter scaffolding that holds it all together. But here's the twist: the great attractor's pull isn't a one-way trip. Thanks to dark energy's repulsive force, the universe's expansion will eventually overpower even this colossal gravity well, leaving future galaxies adrift in an ever-accelerating expanse. For now, though, we're caught in the tide, racing toward a shadowy giant whose secrets remain just out of reach. A reminder that even in our own cosmic backyard, the universe still holds mysteries waiting to be unraveled. Some planets orbit so close to their stars they complete a full year faster than you finish a workday. Kepler 78b, for instance, races around its host star every 8.5 hours at speeds topping 500,000 miles per hour. That's like crossing the distance from Earth to the Moon in under half an hour. But this isn't just a cosmic speed record, it's a death sentence. At this proximity, the planet's surface temperature exceeds 2,000 degrees Celsius, hot enough to vaporize rock into a swirling atmosphere of molten silicate and metal. Imagine standing on a world where the ground beneath your feet is literally boiling away into space, stripped atom by atom by the relentless stellar winds. What keeps these doomed worlds from spiraling into their stars immediately? The same physics that governs Earth's orbit, just pushed to extremes. Kepler 78b's breakneck velocity generates enough centrifugal force to counterbalance the star's gravitational pull, creating a precarious equilibrium. But this dance can't last. Tidal forces from the star slowly sap the planet's orbital energy, drawing it inward over millions of years until it's torn apart. Astronomers have even spotted the telltale signs of disintegration, cometary-like tails of vaporized material trailing behind these planets, visible in ultraviolet light as they're sculpted by stellar radiation. The discovery of these ultra-short period planets rewrote our understanding of planetary formation. Conventional models suggested gas giants couldn't form so close to stars, yet here they are, with some likely being the charred cores of former gas giants whose atmospheres were blasted away. Others might be the remnants of failed binary star systems where one star got consumed, leaving behind a planetary mass ember. Their existence raises provocative questions. Could life ever emerge in such hellish environments, even briefly? Some theorists speculate that under the right conditions, tidally locked planets with permanent day and night sides might harbor slivers of habitability along their twilight zones, though any organisms would face the ticking clock of their world's inevitable destruction. What's equally fascinating is how we detect these speed demons. Traditional methods like transit photometry, watching for a star's dimming as a planet crosses it, work better for short orbits, making these planets easier to spot despite their rarity. Their extreme conditions also leave distinct chemical fingerprints in starlight filtered through their evaporating atmospheres, revealing compositions stranger than any in our solar system. Some show signs of titanium oxide or vaporized iron, elements that would rain as molten droplets before being blown into space. These planetary daredevils offer a glimpse into the fate that might await Mercury billions of years from now as our own sun evolves. They're cosmic laboratories for studying tidal interactions and atmospheric escape, processes that shape all planets but are rarely so dramatic. And for every one we've found, there are likely thousands more, each with its own story of survival against impossible odds until the moment gravity finally wins and a world vanishes in a final incandescent sigh. Deep beneath the mountains of Italy and South Dakota, scientists are hunting for an invisible hurricane, a cosmic gale of dark matter particles thought to be streaming past Earth at 500 kilometers per second. These hypothetical winds, composed of particles that outweigh atoms by at least 10 to 1, could be blowing through your body right now without you feeling a thing. The theory goes like this: as our solar system orbits the Milky Way, it plows through a halo of dark matter particles like a car driving through rain, creating a detectable wind from the direction of the constellation Cygnus. Imagine trillions of weakly interacting massive particles WIMP passing through every square inch of Earth every second, colliding so rarely with normal matter that a human might experience just one interaction in their lifetime. To catch these ghostly particles, physicists have built the most sensitive detectors on Earth: underground vats of liquid xenon shielded from cosmic rays by miles of rock. Projects like Xeno-NNT and LUX Zeppelin operate at temperatures near -100 degrees Celsius, where xenon becomes a dense, ultra-pure liquid capable of flashing with light when a dark matter particle theoretically bumps into its nucleus. The setup is like tuning a microphone to hear a pin drop in a hurricane, requiring isolation from vibrations, background radiation, even the faint radioactivity in the detector's own materials. When a potential interaction occurs, sensors track the faint scintillation and ionization signals, distinguishing potential dark matter events from false alarms like stray neutrons. The challenge: after decades of searching, not a single confirmed dark matter particle detection has been made. Some experiments have reported tantalizing anomalies, like the annual modulation signal observed by Doma/Libra, which some argue could reflect Earth moving through a seasonal dark matter wind as it orbits the Sun. But these remain controversial, with other detectors unable to replicate the findings. The null results have forced physicists to broaden their search beyond WIMP, considering alternative candidates like Action's ultralight particles that might convert to photons in powerful magnetic fields, or primordial black holes left over from the Big Bang. What keeps researchers going is the staggering scale of the mystery. Dark matter outweighs visible matter 5 to 1, sculpting galaxies and galaxy clusters with its gravity, yet refusing to reveal its identity. Every failed detection narrows the possibilities, inching us closer to either a paradigm-shifting discovery or a complete rewrite of cosmic physics. And here's the humbling part: if dark matter interacts even more weakly than current theories predict, our grand underground experiments might be as futile as trying to catch neutrinos with a butterfly net. Yet the hunt continues, driven by the tantalizing possibility that the next flash of light in a xenon tank could rewrite our understanding of reality itself. When Einstein predicted gravitational waves over a century ago, even he doubted we'd ever detect these ripples in spacetime. But in 2015, LIGO proved not only their existence, but that they race across the cosmos at exactly light speed, just as relativity demands. Picture a cosmic pond where dropping a stone creates waves that spread instantly in Newton's universe, but in Einstein's move at a strict speed limit. That fundamental difference changed everything we knew about gravity. LIGO first detection, two black holes colliding 1.3 billion light-years away, showed this cosmic speed limit in action. The merger's gravitational waves arrived precisely when they should have if traveling at light speed, while other observatories confirmed no accompanying light arrived earlier. This wasn't just confirmation, it ruled out Newton's idea of instantaneous gravitational action, proving gravity's news propagates at the same finite speed as light. Imagine yelling across a valley and seeing the person react before your voice reaches them. That's what Newton's gravity allowed and what Einstein's forbids. This discovery held another surprise. While electromagnetic waves like light interact with matter, slowing through glass or scattering off dust, gravitational waves slice through everything. A gamma-ray burst might get absorbed by a gas cloud, but the space-time ripples from the same event would pass through planets, stars, even entire galaxies unperturbed. That's why LIGO detected waves from colliding neutron stars before telescopes saw the light. The waves didn't need to fight through interstellar gas, yet there's a beautiful symmetry here. Both light and gravitational waves are oscillations, one in electromagnetic fields, the other in spacetime itself. Both travel at speed seen not because they're related, but because this speed is baked into the universe's fabric as the maximum rate any influence can spread. The difference: light needs the electromagnetic field to ripple, while gravitational waves are the ripple, literal stretching and squeezing of space dimensions themselves. Newton's gravity couldn't explain this. His laws implied if the sun vanished, Earth's orbit would change instantly. But relativity says we'd keep orbiting the missing sun for 8 minutes until the last gravitational wave, traveling at light speed, delivered the news. This cosmic delay isn't hypothetical. LIGO proved it by catching waves from mergers whose light arrived later. What's truly mind-bending is how pristine these waves remain. After journeying billions of years, they retain perfect fingerprints of their source, whether two black holes spiraling inward or a neutron star's crust cracking. Compare that to starlight, which gets reddened and scattered by cosmic dust. Gravitational waves are the universe's clearest messengers, carrying undistorted whispers from the most violent event since the Big Bang. So while light still rules astronomy, gravitational waves offer something new. A direct line to the universe's hidden symphonies, played at exactly the tempo Einstein predicted. Every merger LIGO detects is another tick on relativity's cosmic stopwatch, proving once again that when it comes to gravity, space and time dance to the speed of light. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with a force so violent its shockwave tears through space at 30,000 kilometers per second. That's 10% the speed of light, fast enough to cross Earth's entire diameter in under a second. But what makes supernova shockwaves truly extraordinary isn't just their speed, it's how they transform destruction into creation, forging the very elements that make up our bodies and our world. Take the Crab Nebula, the ghostly remains of a star that exploded in 1054 AD. Even nearly 1,000 years later, Hubble's time-lapse images reveal its shockwave still expanding outward at over 1,500 kilometers per second faster than most spacecraft as it plows into surrounding gas. The energy is so immense that electrons spiral along magnetic field lines at near light speed, emitting the eerie blue glow we see today. This isn't just cosmic wreckage. It's a particle accelerator the size of a solar system, where hydrogen and helium are crushed together under temperatures exceeding 1 billion degrees to form carbon, oxygen, and even gold. The physics behind these shockwaves reads like an alchemist's dream. As the supernova's blast wave rams into interstellar material, it creates conditions so extreme that atomic nuclei overcome their natural repulsion and fuse. This rapid neutron capture process, or R process, is responsible for half the elements heavier than iron in the universe, from the iodine in your thyroid to the platinum in catalytic converters. Without supernova scattering these forged metals across galaxies, planets like Earth would lack the ingredients for life itself. But here's what's truly mind-blowing. The Crab's shockwave isn't slowing down. As it expands into lower density regions of space, it actually accelerates like a snowball effect in reverse. The outer filaments visible in Hubble images are now moving faster than the inner ones, a phenomenon that defies everyday intuition about explosions. It's a reminder that in space, even destruction operates on scales and timespans we're only beginning to understand. These shockwaves also serve as cosmic signposts. By measuring how their light polarizes, astronomers can map the tangled magnetic fields threading through space fields that guide cosmic rays and shape future star formation. And when a shockwave eventually collides with another gas cloud, the compression can trigger the birth of new stars, turning a stellar graveyard into a stellar nursery. So the next time you see an image of the Crab Nebula's delicate filaments, remember, you're looking at the aftermath of a cosmic bomb that's still exploding, still accelerating, and still seeding the universe with the building blocks of everything we know. Stretching across billions of light years like invisible rivers, the cosmic web's warm, hot intergalactic medium, or WIM, is the universe's hidden highway system, with superheated gas filaments racing through the void at 500 kilometers per second. These aren't just empty channels between galaxies. They're the universe's plumbing, carrying half of all normal matter in the form of ionized gas, so diffuse it's nearly invisible. Picture a spiderweb soaked in water. The strands glisten where droplets cling, but most of the liquid remains suspended, nearly undetectable. That's the WIM, ordinary matter so spread out it took decades for astronomers to even confirm its existence. The Sloan Digital Sky Survey's painstaking maps reveal this shadowy infrastructure. By analyzing how distant quasars' light dims as it passes through these filaments, astronomers detected telltale absorption lines from oxygen 5 and 6 times ionized atoms stripped bare by temperatures between 100,000 and 10 million degrees. The gas moves so fast it could cross the distance from Earth to the Moon in under 20 minutes. Yet it's so thin that a cubic meter might contain just a single atom. At those densities, you could fly a spaceship through it forever and never feel a breeze. What's astonishing is how these filaments dictate the universe's large-scale structure. Gravity sculpted them in the aftermath of the Big Bang, with dark matter acting as an invisible scaffold guiding normal matter into vast, intersecting sheets and threads. Galaxies form where these strands knot together like beads on a string, while the WIM relentless flow funnels fresh gas into galactic hubs, fueling new generations of stars. Some simulations suggest up to 90% of galaxies' future star-forming material is still locked in these intergalactic currents, waiting to be pulled into the luminous nodes we see today. Yet the WIM isn't just passive plumbing, it's a record keeper. Its composition holds clues to cosmic evolution, with heavier elements like carbon and nitrogen betraying their origins in ancient supernovae. When galaxies collide or quasars erupt, they inject these metals into the filaments, creating a chemical fingerprint that traces the universe's violent history. X-ray telescopes like Chandra have spotted these enriched regions glowing faintly where filaments intersect, like streetlights marking cosmic intersections. The real challenge, mapping something so tenuous. Astronomers use tricks like the Sunyaev-Zeldovich effect, measuring how the WIM subtly distorts the cosmic microwave background, or hunt for faint X-ray emissions when filaments brush against galaxy clusters. It's like trying to map a breeze by watching how it bends candle flames across a continent. But each new detection peels back another layer of the universe's hidden anatomy, revealing the currents that have shaped everything from the largest galaxy clusters to the smallest dwarf stars. So next time you gaze at a deep field image of galaxies, remember, the sparkling points of light are just the glitter on the surface. The real action lies in the invisible torrents between them, the rivers of fire slowly carving the universe into shape. Imagine a star with a crust so dense a teaspoon of it would weigh 1 billion tons. Now picture that crust suddenly cracking like an eggshell under unimaginable pressure. This is the reality of magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. When their rigid surfaces rupture in violent starquakes, they unleash gamma-ray flares so powerful they can temporarily outshine every star in the Milky Way combined, all in a fraction of a second. These aren't just cosmic temper tantrums, they're some of the most energetic events since the Big Bang, driven by physics at the absolute edge of what's possible. The physics behind these explosions is both simple and mind-bending. A magnetar's crust made of neutron-rich material harder than diamond floats on a superfluid core. As the star's insane magnetic field twists a process called magnetic braking, it strains the crust until it snaps. The energy released is staggering. A single starquake can discharge more energy than our sun emits in 150,000 years. But here's the wild part, because the crust is so dense, these fractures propagate at nearly half the speed of light. Picture an earthquake where the seismic waves travel fast enough to circle Earth 7 times in 1 second. These ruptures create fireballs of electrons and positrons accelerated to near light speed along twisted magnetic field lines. When these particles collide, they annihilate in bursts of gamma rays, the universe's most energetic form of light. The 2004 gamma-ray flare from Magnetar SGR 1806, located 50,000 light-years away, was so intense it ionized Earth's upper atmosphere from another galaxy. Satellites designed to detect nuclear explosions actually thought it was a nearby supernova. Yet Magnetar flares aren't just destructive, they're cosmic gold mines for physicists. Their X-ray afterglows carry fingerprints of quantum electrodynamics operating in extreme magnetic fields, offering glimpses of how matter behaves under conditions impossible to recreate on Earth. Some theories even suggest these flares might be responsible for a fraction of the mysterious fast radio bursts that puzzle astronomers, linking two of space's most enigmatic phenomena. The real puzzle is how magnetars form in the first place. Only about 30 are known in our galaxy, suggesting they're either rare or short-lived. Some might be born from supernova where the collapsing star's rotation and magnetic field align just right to create this stellar extreme. Others could start as fast-spinning pulsars that gradually amplify their magnetic fields over millennia. Either way, their existence proves the universe has a flair for the dramatic turning stellar corpses into celestial grenades just waiting to detonate. So the next time you hear about a gamma-ray flash from deep space, consider the possibility. It might be a magnetar's crust shattering under forces we can barely comprehend, sending ripples of energy across the cosmos at the speed of light. And somewhere in the aftermath of that cataclysm, new secrets about the universe's most extreme physics are waiting to be decoded. Voyager 1 may be crawling at a cosmic snail's pace, just 38,000 miles per hour compared to hypervelocity stars or relativistic jets, but this tiny human-built probe is doing something no other spacecraft has ever achieved, breaking free from our sun's gravitational grip and venturing into the unknown between stars. Launched in 1977 with a mission to study Jupiter and Saturn, Voyager 1 long outlived its original purpose, becoming humanity's first emissary to interstellar space. Its current speed wouldn't even get you to the moon in 6 hours, yet it's carrying something far more precious than velocity: the golden record, a time capsule of Earth sounds, music, and images, destined to drift among the stars for potentially billions of years. The sheer scale of Voyager's journey puts its speed in perspective. Even at its modest pace, it crossed the orbit of Pluto in 1990, though the dwarf planet itself was elsewhere in its orbit, and in 2012 it pierced the heliopause, the boundary where the sun's influence wanes and interstellar space begins. This transition wasn't marked by some dramatic barrier, but by a shift in the weather. The solar wind's charged particles faded, replaced by the denser, cooler plasma of the galactic medium. Scientists knew Voyager had left home when its instruments detected a sudden spike in cosmic rays and a drop in solar particles, proof it was swimming in the ocean of the Milky Way rather than the sun's backyard pond. What's astonishing isn't just Voyager's distance, but its endurance. Powered by 3 radioisotope thermoelectric generators, essentially nuclear batteries converting plutonium's decay heat into electricity, the probe still communicates with Earth, its 23-watt signal taking over 22 hours to reach us. That signal, weaker than a refrigerator light bulb by the time it arrives, is captured by NAS, a deep space network antennas, which must listen with excruciating precision to pick Voyager's whisper out of the cosmic noise. The golden record elevates Voyager from a machine to a message. Etched onto a copper disc coated in gold are 115 analog images, spoken greetings in 55 languages, and 90 minutes of Earth's greatest music from Bach to Chuck Berry. The record's cover includes symbols explaining its origin and how to play it, a cosmic hello to any civilization that might one day intercept it. While the odds are vanishingly small that it'll ever be found, the record stands as a testament to humanity's yearning to connect, even if across eons and light years. Voyager's true legacy isn't speed but persistence. In 40,000 years, it'll drift within 1.7 light-years of a star in Ursa Minor, still nowhere near another planetary system, but carrying our stories farther than any artifact in history. Long after its power fades and its instruments fall silent, it'll keep coasting through the void, a silent witness to a species that once looked up and dared to send a piece of itself into the infinite. At the heart of a black hole's overwhelming gravity lies one of the universe's most violent racetracks, the accretion disk. This swirling maelstrom of superheated gas and plasma doesn't just orbit the event horizon. It spirals inward at velocities approaching the speed of light, stretched and twisted by tidal forces beyond human comprehension. The Event Horizon Telescope's groundbreaking image of M87 star's shadow revealed this chaos in stunning detail. A lopsided ring of orange-hued plasma, brighter on one side as relativistic effects magnify the light from material racing toward us at near light speed. Picture the inner edge of that disk like a cosmic waterfall. Gas molecules that spent millennia drifting through space now find themselves caught in a gravitational sprint where time and space warp under Einstein's rules. Just outside the event horizon, matter can orbit at 60% light speed, fast enough to circle Earth's equator 7 times in a single second. As particles rub against each other in this extreme environment, friction heats the disk to millions of degrees, causing it to glow brightly across the electromagnetic spectrum from radio waves to X-rays. What makes these disks truly mind-bending is how they distort our view of physics. Doppler beaming, the same effect that makes a siren's pitch change as it passes, causes the side rotating toward us in M87 star's disk to appear dramatically brighter, while the receding side dims into near invisibility. Meanwhile, the black hole's spin drags spacetime itself around like syrup on a spoon, forcing the inner disk to precess in wild loops. Some simulations suggest that under these conditions, magnetic fields become so twisted they launch jets of particles perpendicular to the disk at 99% light speed, creating the universe's most powerful particle accelerators. The closer you get to the event horizon, the stranger the disk behaves. Time dilation means an observer far away would see infalling material appear to freeze at the edge. Red shifted into invisibility as photons struggle to escape the gravitational well. Yet from the plunging gas's perspective, it crosses the horizon in an instant, spaghettified into a stream of atoms by tidal forces that could stretch a human body into a strand thinner than a DNA helix. These disks aren't just destruction engines, they're cosmic alchemy labs. The intense heat and pressure near the inner disk forge heavy elements like gold and uranium, which are later flung into space by jet outflows or disk winds. Some theories even suggest that certain supernovas' unusual brightness comes from black hole disks forming inside dying stars, converting gravitational energy into light with terrifying efficiency. The Event Horizon Telescope's next targets, including our own Milky Way's quieter black hole, Sagittarius A star, promise to reveal how disk dynamics change with size and spin. Already, subtle differences in M87 star's disk structure hint at complex magnetic fields and turbulence that could rewrite models of how black holes feed. Every flicker and warp in these luminous rings carries encoded secrets about gravity's ultimate stronghold and the extreme physics that govern the universe's darkest hearts. The universe's first moments weren't just fast, they defied the very laws of physics as we know them. In the tiniest sliver of time after the Big Bang, a trillionth of a second, space itself exploded outward in a growth spurt so violent it would make hypervelocity stars look like they're standing still. This was cosmic inflation, a period where the universe didn't just expand, it ballooned faster than light could travel, doubling in size at least 90 times over in less time than it takes for a photon to cross a single atom. How do we know this happened? The evidence is etched into the oldest light in existence, the cosmic microwave background, or CMB. This faint glow, visible to radio telescopes as static from the edge of the observable universe, is the cooled remnant of the Big Bang's fireball. But look closer and you'll notice something peculiar. The CMB's temperature is nearly identical in every direction, varying by less than 1 part in 100,000. That uniformity is impossibly smooth unless the universe underwent a phase where distant regions were once close enough to equalize temperatures before being ripped apart by inflation's runaway expansion. Think of it like stretching a crumpled plastic sheet until every wrinkle vanishes. Inflation took quantum fluctuations, microscopic ripples in space-time, and stretched them to cosmic scales, seeding the galaxies and voids we see today. The same process that smoothed the universe also left faint fingerprints in the CMB's polarization patterns, subtle swirls detected by telescopes like Planck and Bicep. These primordial gravitational waves, if confirmed, would be direct tremors from inflation's final moments, when the universe's exponential growth screeched to a halt and dumped its energy into creating matter and radiation. But here's the twist: inflation didn't break relativity's speed limit. Space itself can expand faster than light because no information or matter is actually moving through space. It's the fabric between points stretching. Like dots on an inflating balloon, galaxies aren't racing apart. The space between them is growing. This loophole explains how regions of the universe now separated by 93 billion light-years could once have been in thermal contact. The implications are staggering. If inflation's energy field, dubbed the inflaton, decayed unevenly, it could have spawned an infinite multiverse where bubble universes with different physical constants constantly bud off from an eternally inflating background. Our observable universe might just be one bubble in an endless froth, and yet inflation remains a theory, albeit the leading one, because we can't yet peer past the CMB's curtain. Future telescopes measuring the CMB's polarization with even finer precision might finally catch inflation's smoking gun, a specific curl pattern in the light's orientation. Until then, this brief but universe-shaping epoch remains one of cosmology's greatest triumphs and its deepest mysteries. So when you see a map of the CMB's temperature variations, you're not just looking at the afterglow of creation. You're seeing the echo of a time when the universe rewrote its own rules, expanding so fiercely that it set the stage for everything to come: stars, planets, and even the curiosity that lets us ponder it all. When two neutron stars collide, they don't just create gravitational waves. They unleash a storm of nuclear fire that sprays heavy metals across the cosmos at 1/10 the speed of light. These kilonova ejecta are nature's ultimate foundries, forging elements like platinum, gold, and uranium in the most extreme conditions since the Big Bang. Picture the aftermath of such a collision: a glowing, iridescent cloud expanding at over 67 million miles per hour, its outer layers laced with neutron-rich material condensing into exotic isotopes heavier than anything formed in ordinary supernova. What makes these events so potent is the sheer density of the material involved. Neutron stars pack more mass than our Sun into a sphere the size of Manhattan, meaning even a teaspoon of their crust contains enough compressed matter to weigh as much as Mount Everest. When two of these ultra-dense objects spiral together and merge, their outer layers get shredded by tidal forces, flinging neutron-rich matter into space at relativistic speeds. The ejected material undergoes rapid neutron capture-the-R process, where atomic nuclei gulp down free neutrons faster than they can decay, climbing the periodic table to form elements like platinum in seconds. This process leaves a distinct fingerprint. The expanding debris glows blue at first from radioactive decay of lighter elements, then shifts to red as heavier isotopes like uranium take over. Astronomers observed this exact color evolution in GW 170817, the kilonova detected alongside gravitational waves in 2017. Spectroscopy revealed telltale absorption lines of strontium and other heavy metals, confirming these collisions as cosmic gold mines literally. But the real surprise is how far this material travels. At 10% light speed, ejecta can cross a light year in just a decade, seeding interstellar clouds with precious metals. Some estimates suggest a single kilonova might disperse enough gold to gild every planet in a galaxy. Over billions of years, these events have enriched the cosmos with the heavy elements essential for planets and life. The uranium in Earth's crust, the platinum in catalytic converters, even the iodine in your thyroid, they all likely originated in neutron star collisions that happened long before our solar system formed. Yet kilonovae aren't just element factories. Their high-speed ejecta also shape their surroundings, plowing into interstellar gas and triggering shockwaves that can compress nearby clouds into new stars. It's a cosmic feedback loop. The same explosions that forge metals also create nurseries where those metals might one day be incorporated into planets. And because neutron star mergers are rare, occurring roughly once every 100,000 years per galaxy, each one leaves a distinct chemical signature, like a radioactive timestamp marking its contribution to galactic evolution. The next generation of telescopes, like the Vera Rubin Observatory, will hunt for these glowing remnants across the universe, piecing together how often they occur and how much they've contributed to the periodic table. Every kilonova spotted is another clue in the mystery of where the universe's heaviest elements come from, and how their fleeting, high-speed journeys have shaped everything from distant galaxies to the device you're using right now. We're racing through the cosmos right now, not just as individuals, not just as a planet, but as an entire solar system, hurtling around the heart of the Milky Way at 500,000 miles per hour. That's fast enough to cross the distance from Earth to the Moon in just 30 minutes, yet from our perspective, it feels like standing still. This isn't science fiction, it's the reality of our place in the galaxy. Every star, planet, and speck of dust in our solar system is locked in a grand, spiraling dance around the galactic center, a journey so vast it takes 230 million years to complete just one full orbit. The last time Earth was in this exact position, dinosaurs were just beginning their reign, and the Atlantic Ocean was barely a crack in the planet's crust. Our path isn't random. The Milky Way's gravity, anchored by Sagittarius, a star, the supermassive black hole at its core, holds us in this cosmic waltz. Picture the galaxy as a spinning vinyl record, with our solar system orbiting about halfway between the center and the edge, tucked into a minor spiral arm called the Orion Spur. From here, the Milky Way's core blazes with the light of billions of stars, while the outer reaches fade into darkness. But don't let the word minor fool you. The Orion Arm is still thousands of light years across, sprinkled with stellar nurseries like the Orion Nebula, where new stars are born from collapsing gas clouds. This motion isn't perfectly smooth. Just as Earth's orbit around the Sun has slight wobbles, our solar system bobs up and down through the galactic plane as we travel, completing a vertical oscillation every 60 million years. Some scientists speculate these periodic dips might influence Earth's climate. When we pass through denser regions of interstellar gas and dust, it could subtly affect our planet's exposure to cosmic rays, potentially triggering shifts in biodiversity. What's truly humbling is how small our speed feels on the galactic scale. Even at 500,000 miles per hour, our solar system is crawling compared to hypervelocity stars or quasar jets. Yet this stately pace has carried us around the Milky Way about 20 times since the Sun first ignited. Each orbit etches our story deeper into the cosmos, a story written not just in starlight, but in the slow, silent arcs of gravity's unbreakable hold. So the next time you look up at the Milky Way's hazy band stretching across the night sky, remember, you're not just gazing at the galaxy, You're flying through it, part of a celestial caravan that's been on this same road for billions of years and will keep rolling long after we're gone. White dwarfs aren't just stellar corpses, they're cosmic cannonballs. When these dense remnants of sun-like stars meet a violent end in asymmetric supernova, they can get kicked across the galaxy at speeds topping 2,000 kilometers per second, fast enough to cross the continental United States in under 2 seconds. Imagine a celestial bullet the size of Earth, packing half the mass of our sun, rocketing through space with enough velocity to escape the Milky Way entirely. This isn't science fiction, it's the reality of Type 1, a supernova, where a perfectly balanced explosion becomes nature's ultimate slingshot. The secret lies in the physics of detonation. Most Type 1, a supernova occur when a white dwarf siphons too much material from a companion star, pushing past a critical mass limit. But if that explosion ignites slightly off-center, like a firecracker bursting more violently on one side, the resulting recoil can launch the surviving remnant at mind-bending speeds. Picture standing on a skateboard and throwing a bowling ball forward. You'd roll backward with equal force. Now scale that up to stellar proportions. The white dwarf is the skateboard, and the bowling ball is half its mass ejected at 10,000 kilometers per second. The math is unforgiving. Conservation of momentum demands the leftover core gets punted in the opposite direction. Astronomers have spotted these hypervelocity white dwarfs crisscrossing the Milky Way, their extreme speeds betraying their explosive origins. One notable example, SDSS J123+06 star, streaks through space at over 1,500 kilometers per second, trailing a wake of ionized gas like a ghostly comet. Its trajectory points back to the galactic disk, suggesting it was launched from a supernova millions of years ago. These rogue remnants serve as cosmic breadcrumbs. By tracking their paths, scientists can reverse engineer the explosions that birthed them, uncovering clues about stellar chemistry and the precise mechanics of supernova asymmetry. But their usefulness doesn't end there. Hypervelocity white dwarfs double as galactic speedometers. Because they're ejected with predictable energies, their current velocities reveal how much the Milky Way's gravity has slowed them down over time, effectively measuring the galaxy's mass distribution. It's like throwing a ball straight up and calculating Earth's gravity by how fast it decelerates, except here the ball is a trillion-ton stellar remnant, and the experiment spans light years. Recent studies using these white dwarfs suggest our galaxy may harbor more dark matter than previously thought, their trajectories tugged by invisible mass we can't otherwise detect. What's truly poetic is how these dead stars illuminate the living universe. Their speeds encode secrets about galactic structure, supernova physics, and even the nature of dark matter, all from the silent, unchanging glow of a cooling ember racing through the void. So the next time you hear about a white dwarf, remember, some aren't just fading quietly into the night. They're surfing shockwaves from their own deaths, riding supernova blasts into the cosmic unknown. Einstein famously called it spooky action at a distance, quantum entanglement, the bizarre phenomenon where two particles become so deeply linked that measuring one instantly determines the state of the other, no matter how far apart they are in the universe. Imagine flipping a coin in New York, and at that exact moment, a coin in Tokyo lands on the same side without any signal passing between them. This isn't just theoretical. Laboratories regularly entangle particles separated by hundreds of miles, confirming the effect happens at least 10,000 times faster than light could travel the same distance. The mechanism defies everything we know about classical physics. When two particles become entangled, often through interactions like photon emissions or quantum decay, their properties like spin or polarization become interdependent. Until measured, they exist in a ghostly superposition of all possible states. But the moment one particle is observed, its twin snaps into a corresponding state faster than any information could bridge the gap between them. It's as if the universe maintains an invisible ledger, updating entries simultaneously across cosmic distances without any obvious messenger. What makes this truly mind-bending is that it doesn't violate relativity's cosmic speed limit. No actual information or energy transfers between the particles. The correlation is immediate but can't be controlled or exploited to send messages faster than light. Think of it like opening a sealed letter and discovering its contents match another unopened letter light years away. The decision was made the moment they were sealed, even if the revelation feels instantaneous. This distinction keeps quantum entanglement from breaking causality while still showcasing physics' deepest strangeness. Recent experiments have pushed entanglement to staggering extremes. Chinese satellites have beamed entangled photons to ground stations 1,200 kilometers apart, maintaining their spooky connection through Earth's turbulent atmosphere. Others have entangled not just photons but whole atoms, diamonds, even tiny mechanical oscillators visible under microscopes. Some theories even suggest entanglement might scale up, that macroscopic objects, given perfect isolation, could exhibit these quantum links, though decoherence from environmental interference makes this extraordinarily difficult to observe. The implications ripple across technology and philosophy alike. Quantum networks leveraging entanglement could revolutionize secure communications. Any eavesdropping attempt would disturb the delicate quantum states, exposing intruders. Quantum computers use entangled qubits to perform calculations impossible for classical machines, factoring enormous numbers or simulating molecular interactions with unprecedented precision. Some physicists speculate that entanglement might be fundamental to spacetime itself, with the fabric of the universe emerging from a vast web of quantum connections, a concept known as it from bit. Yet mysteries remain. Why does measurement collapse the quantum state? Could entanglement somehow underpin gravity or dark energy? And most hauntingly, if the universe began in a single quantum state, is everything still subtly entangled on some level, with particles separated by billions of light years secretly dancing to the same quantum tune? We're only beginning to unravel these questions, but one thing is certain. In the quantum realm, speed isn't just about motion. It's about the instantaneous, invisible threads stitching reality together in ways that still leave even the brightest minds awestruck. Galactic collisions sound like cosmic demolition derbies, two massive star systems smashing together in a cataclysmic crunch. But the reality is far stranger and far more beautiful. When the Milky Way and Andromeda galaxies collide in about 4 billion years, their stars will streak past one another at nearly 500,000 miles per hour, yet almost none will actually collide. Picture two swarms of bees merging in midair, where each bee represents a star separated by trillions of miles of empty space. Despite the mind-bending speeds, the sheer distance between stars means they'll slide past each other like ghosts, pulled into an intricate new dance by gravity's unseen hand. The numbers behind this slow-motion merger are staggering. Andromeda, our closest galactic neighbor, is racing toward us at 250,000 miles per hour, drawn by mutual gravitational attraction. When the two galaxies finally meet, their combined 2 trillion stars will begin a stately spiral over billions of years, stretching and warping each other's shapes with tidal forces. Supercomputer simulations show the Milky Way's orderly disk shredding into luminous streamers, while Andromeda's core, a trillion-star behemoth, plows through our galactic plane in a gravitational tug of war. The real fireworks will come from the gas clouds between stars, slamming together at supersonic speeds and igniting a firestorm of new star formation. This isn't destruction, it's reinvention. Over time, the two galaxies will twirl around each other in ever-tightening loops, their stars mingling into a single elliptical galaxy nicknamed Milkdromeda. Our solar system, if it survives intact, will likely be flung into a wider orbit far from the galactic core. The night sky will transform beyond recognition, Andromeda's stars will blossom from a faint smudge into a dazzling band stretching horizon to horizon, before gradually blending with the Milky Way's own stars into a new cosmic tapestry. What's truly humbling is how serene this apocalypse will be for any future inhabitants of Earth. The odds of our Sun colliding with another star during the merger are less than 1 in a billion. Even the galaxy's central black hole Sagittarius and Andromeda's equally monstrous counterpart will take millions of years to spiral together, eventually merging in a gravitational wave outburst detectable across the universe. This slow-motion ballet holds clues to galaxies past and future. By studying similar mergers like the antennae galaxies, astronomers see how collisions recycle gas into new stars and redistribute heavy elements. Some theorize our own Milky Way spiral arms might be scars from ancient collisions with dwarf galaxies, and when Andromeda finally settles, it will stand as a monument to gravity's patience, a testament to how the universe builds beauty through chaos, one careful collision at a time. Light speed isn't just fast, it's the universe's ultimate speed limit, a cosmic rule etched into the fabric of reality itself. At 300,000 kilometers per second, a photon could circle Earth's equator 7.5 times in the blink of an eye. Yet for all its mind-bending velocity, light's speed isn't arbitrary. It's the maximum rate any influence, any signal, anything can propagate through spacetime. This isn't a limitation of technology or engineering. It's a fundamental property woven into Einstein's equations, where energy and mass twist spacetime into a geometry that simply won't allow shortcuts. The secret lies in mass, or rather, the lack of it. Photons, the particles of light, are massless, which means they don't just move at light speed, they are light speed, their existence inseparable from their velocity. For particles with mass, the story flips. As you accelerate an object closer to light speed, its mass effectively increases, demanding ever more energy to push it further. Hitting that final percent, it would take infinite energy, a cosmic stop sign no amount of engineering can bypass. Imagine a treadmill that speeds up every time you match its pace. You'd never reach the end. That's the dilemma matter faces in a relativistic universe. But what if we could cheat? Enter the Alcubierre warp drive, a theoretical concept where spacetime itself becomes the engine. Proposed by physicist Miguel Alcubierre in 1994, the idea skirts Einstein's speed limit by contracting space in front of a ship while expanding it behind, creating a bubble where the vessel rides a wave of distorted spacetime. Inside this bubble, the ship wouldn't move faster than light. It would bring its destination closer, like a surfer riding a folding wave. The math checks out, but the catch is staggering. Powering such a drive would require negative energy exotic matter with repulsive gravity, something we've never observed naturally. Here's where it gets even trickier. Even if negative energy exists, the Alcubierre drive comes with cosmic side effects. The warp bubble's leading edge would concentrate enough energy to vaporize anything it touches, while particles caught in its wake would release lethal bursts of Hawking radiation upon arrival. And then there's causality. Arriving before light from your departure could create paradoxes, violating the very laws the drive seeks to exploit. Some theorists suggest these might be more than engineering hurdles. They could be nature's way of enforcing no-go zones in physics, like firewall warnings against breaking reality. Yet the dream persists, not because warp drives are plausible with today's science, but because they reveal how much we still don't understand about spacetime's flexibility. Quantum entanglement already shows particles communicating instantly across distances, hinting that spacetime might be more emergent than fundamental. And in the depths of black holes or the early universe's inflationary expansion, we catch glimpses of physics operating outside our comfort zone. Light speed may be today's limit, but the universe has a habit of surprising those who dare to question its rules. So while we're stuck for now with solar sails and ion drives, the lesson isn't about resignation, it's about inspiration. Every photon racing from a distant star, every cosmic ray screaming through the void, reminds us that speed isn't just a number. It's a window into the universe's deepest workings, a puzzle waiting for the next Einstein or the next Alcubierre to crack it open. From hypervelocity stars escaping galaxies to particles racing at 99.99999999999% light speed, the universe operates on a scale of motion that defies human intuition. These aren't just cosmic curiosities, they're the fundamental processes shaping existence itself. Gamma-ray bursts rewrite galactic chemistry in seconds. Black hole jets sculpt galaxy clusters over eons, and even the seemingly static cosmic web flows with rivers of million-degree gas. Every extreme speed record we've explored reveals another piece of the puzzle: how energy flows, how matter organizes, and how the cosmos evolves from chaos into structure. Consider the irony: our entire Milky Way spins at 500,000 miles per hour, yet we perceive it as fixed while chasing an invisible gravitational titan. Neutron star collisions forge gold at relativistic velocities, while dark matter may be blowing through you right now at undetectable speeds. The universe doesn't just tolerate these extremes, it thrives on them, using velocity as both sculptor and destroyer. From the inflationary Big Bangs faster than light expansion to quantum entanglement's instantaneous links, speed defines reality's very framework. And where does that leave us? On a pale blue dot orbiting a mediocre star, watching these cosmic sprinters from the sidelines. Yet here we are decoding black hole jets with telescopes, catching gravitational waves with lasers, even sending our own tiny probes toward interstellar space. Our place isn't just as observers, but as creatures shaped by these same violent processes. The iron in your blood came from a supernova's shockwave. The gold in your jewelry was forged in a neutron star collision. Every atom in your body holds echoes of the universe's most spectacular speed demons. So tell us, which of these cosmic velocity records left you awestruck? Was it the rogue black holes surfing at 5 million miles per hour, or perhaps the oh my god particles near light speed impact? Share your thoughts below, and remember, the next time you look up at the night sky, you're not just seeing stars. You're witnessing the aftermath of the universe's greatest races, where the finish line is light years away, and the competitors are the very forces that built reality itself.